Introduction. Hydro-geomorphology is primarily a matter of water and sediment. This constitutes the study of hydrological processes, as well as of the soil and streambed erosion processes, imperative. Surface runoff, base flow, stream discharge, soil erosion and sediment transport constitute the basic interrelated natural processes, which perpetually chisel the geomorphological profile of a basin. In most cases, it takes hundreds or even thousands of years for any effect to take its toll on the geomorphological profile of the Earth. However, it is worth studying the hydrogeomorphological processes at a continuous timescale. Apart from the quantification of the hydrological processes, as well as of the soil and streambed erosion processes, the continuous hydrogeomorphologic modeling provides valuable information for the future trend of these physical processes. There is a wide variety of integrated models that continuously simulate the runoff, soil erosion and sediment transport processes. Just a few of these models are listed below. Most of these models are available in their software form. Answers is a physically based, distributed model. Although the model was initially developed to operate on an event basis, it underwent modifications to be used for continuous simulations as well. The current version of Answers can continuously simulate runoff by means of the Holton or the Green and amped infiltration methods. The continuity equation is the basic equation used for the computation of surface runoff. Where's the volume of water in storage, surface detention, tis the time, e's the inflow rate and wa the outflow rate. Soil erosion is modeled by estimating raindrop detachment using rainfall intensity and universal soil loss equation, USLE, factors. As far as sediment transport is concerned, Yallin's bedload transport equation is used. Where tis the transport capacity by surface runoff, cis the surface slope and key's the flow rate per unit width. Yallin's equation was originally conceived for the routing of sediments through a channel. However, several attempts have been made towards the application of this channel formula for overland flow. Amongst these, Foster and Meyer, as well as Alonso et al., proved that Yallin's equation can successfully be applied for sediment transport by surface runoff. AGMS is a conceptual distributed model, which operates on a cell basis. AGMS was also initially developed for event-based simulations. Latest versions of the model, though, offer the ability for long-term hydrologic and soil erosion simulations. The modeling of runoff is based on Soil Conservation Service, SCS curve number, CN, method, Section 4.1. Soil erosion and sediment transport on the soil surface are modeled using the revised Universal Soil Loss Equation, RUL. Where AI is the average soil loss per unit area and time, RES the rainfall erosivity factor, K is the soil erodibility factor, LES the slope length factor, SIS the slope steepness factor, SIS the cover and management factor and PIS the support practice factor. The RUL is exactly the same with USL. The only difference between RUL and USL is that the factors K, L, S, CAN P, in RUL, are computed in more detail. Sediment routing in streams is modeled by a modified Einstein deposition equation and the Bagnall suspended sediment formula for stream sediment transport. Another physically based model which can continuously simulate the hydrogeomorphological processes, at the basin scale, is the Chemical Runoff and Erosion from Agricultural Management Systems model, CREAMS. As in the case of AGMS, runoff modeling in CREAMS is based on the SCSCN method for the estimation of hydrologic losses due to infiltration and kinematic surface water flow equations. The peak runoff rate is computed by the following equation. Where QP is the peak runoff rate, M3/S, DAS the drainage area, KM2, G's the channel slope, K's the daily runoff volume, and L's the length-width ratio of the basin. The erosion component maintains elements of the USL but includes sediment transport capacity for overland flow, which is estimated by the steady-state continuity equation. Where QS is sediment discharge per unit width, XI is the distance downslope, M, DL is the lateral inflow of sediment and DF is the detachment or deposition of sediment by flow. The composite mathematical model, CMM, applied in this study, comprises three submodels, a rainfall runoff submodel, a submodel for the simulation of soil erosion and a sediment transport submodel for the routing of sediments in streams. The rainfall runoff submodel that is used for the computation of the overland flow, as well as of the flow in the main streams of the subbasins, is the conceptual, semi-distributed hydrologic model HEC HMS 4.2. The soil erosion submodel, utilized for the estimation of soil erosion in a sub-basin, is based on the relationships of Poisson. The estimate of sediment yield at the outlet of a sub-basin, and finally at the outlet of the whole basin, is achieved by means of the stream sediment transport model of Yang and Stahl. The CMM was applied to Cocinthos River Basin and to Nestos River Basin. The application of all three models results in continuous hydrographs and sediment graphs at the basin outlet. The computed stream discharge and sediment discharge values are compared with field measurements, and all models are evaluated as to their competence of simulating the hydro-geomorphological processes in a basin. The geomorphology of the Earth's surface is shaped by physical, chemical, biological as well as geological processes. This lecture focuses on the effect that the physical processes have on the geomorphological profile of a soil surface. The component of physical processes mainly refers to the hydro-geomorphological processes,